So later on, Planck find out he can try to reproduce the experimental curve we find out in our previous lecture here, this curve, simply assuming that the radiation is quantized in terms of the different kind of the discrete energy packet. And this discrete energy depend on the frequency. So for example, one of them is 1 HF. So F is the frequency of the black body radiation, or the photon you will see later, or 2 HF. So you have specific value of the energy. So which means you don't have 1.5 or 1.2 HF for the energy of the radiation. So which means that the energy is quantized. And this H is a constant called the Planck constant. And you can see this is a very small number. So the Planck first find out, okay, by assuming this one, then the curve can perfectly explain. But at the very beginning, people cannot really accept this concept. And I'm going to introduce the reason why. But before that, let's have our first conceptual quiz first. So if the energy is quantized in terms of the E equal to HF, then let's try to study that what has more energy over the photon. So here I give you the wavelengths, yeah? And I also give you the color of the light. So now the answer is D. So you will find out if the energy is quantized, which means it is determined by the frequency. And we know that the frequency of the blue is the higher than the red light. So the higher the frequency, the bigger the energy it is. So the answer is D. But this is based on the quantization of the light. So now also let me also give you the examples. And you can have a better understanding. Even those at the moment of time, people do not really take Planck's calculations seriously at the very beginning, but why his calculation can be used to fit the curve. So Planck mentioned that now the radiation is composed of a different kind of quantized energy. So here I'm going to use a concept we learned before. So at the very beginning, you may do not know the reason why. So let me give you a sense of feeling. Each quantization of energy is fixed, and they can be described and approximated in terms of the motion of the harmonical oscillator. I understand that this one may not be that straightforward for a lot of you, but in order to explain that, I probably have to cover a lot of math details. So I just want to let you know that for each of the quantized energy, they can use the simple harmonical oscillator we learned before to calculate, to approximate the energy. And when you have the different kind of the discrete quantized energy, 1, 2, 3, 4, each of the quantized energy corresponding a specific simple harmonical oscillators. So ideally, this curve can be fit by a distribution and combination of the simple harmonical oscillators. So that's the reason I'm going to study this example here, and that is why at the very beginning when you look at this example, you will say this is a pure classical one. The answer is yes, for this one is pure classical. But the reason it is pure classical is that they only corresponding to one of the discrete symmetries. But if you have a distribution of the harmonic oscillator, you will find out you are not able to create a continuous of them. So each of them will corresponding to one kind of energy spectrums. So let's start to solve this problem. So now this is for just one of them, one of the simple harmonic oscillator for one of the quantized energy. So suppose that for this spring attached to the mass system, when you try to stretch them, they will oscillate. Yeah? So you remember that there will be a V maximum. So they will reach the highest velocity when they reach to the equilibrium position. And the reason is that all the potential energy was converted to the kinetic energy. So the concept you learn still useful here. So the maximum speed is 0.95 meter per second, and the mass is 1.2 kilogram and the spring constant is 35. So in the question A, they want you to find out the frequency of the oscillation and the total energy of this mass spring system. So maybe some of you already noticed that. You see, the frequency of the oscillation. What is the meaning of the frequency of oscillation? This is the frequency of oscillation for these simple harmonic oscillators. And they say, what is the energy of these spring mass systems? Then you're going to calculate. This is the E value here. So you see that is right, that now you can use the simple harmonic oscillators calculation to fit the curve. And that is actually the approach adopted by the Planck. So now we want to calculate the frequency based on the information I just provide you. So you know the spring constant, mass, and the maximum velocity. So let's try to calculate the F. But what is the F? Because this is a simple harmonic oscillation, so you know that you can relate it to the so-called angular velocity. What is angular velocity? This is 2 pi f. So if you forgot this relation, but let's give a check when we study about the concept of rotation. And we also have told you, I also have to teach you that this omega actually can be related to the spring constant divided by the mass of the hanger and take the square root of that. So from this relation, you can calculate that the frequency of this simple harmonical oscillator is actually this term. So K is given, the mass is given, so you can calculate the frequency for these simple harmonical oscillators. So even those at this moment, you're the first time you're learning about quantum physics, so it may take time for you to digest, but you can treat them, this is just one of the quantized photon, one of the quantized energy. And now, what is the total energy of the system? We know that the maximum velocity means that all the potential energy was converted to the kinetic energy. Yeah? So the kinetic energy of the mass spring system, or the mass, is 1/2 m times v maxima square. So you will say, how about the mass of the spring? So normally we just ignore the mass of the spring because it is most of the time negligible. So now the total energy of the mass spring system is 0.454 joules. So now we already find out the frequency and the total energy. The second problem, I want you to determine the size of one quantum energy in these systems. And assume that this energy of the system satisfies this one. So what you calculate E total is En. So which means that this system is made of m particles of the HF. So what the B and C implies to you is that you can also give a check that this formula, when you try to calculate using the HF, then this is the energy carried by the quantized energy, or the photon you will see later. It is not the same as this one. So which means the system is made of m particles of this quantized energy. So now let's try to study using the F we just calculated. So you can calculate that the energy carried by one single quantized energy is this value. But because the total energy is much bigger than this one, yeah? So how many particles, the same simple harmonical oscillators you will need in order to explain the total energy here? You will find out you need at least 10 to power of 33rd particles. But here I just give you a concept. In order to fit the curve, the black body curve, they don't necessarily have to made of the for example here, the 10 to power 33 HF. So each simple harmonical oscillator has their own energy. So this is just one of them. So here the example simply just assume the spectrons can be fit by one of the quantized energy. But the answer is for sure no. So what the Planck is doing that he has to calculate the energy by different kind of the simple harmonical oscillators, each of them has their own HF. Then the total energy of that spectrons actually can be a combination or be fitted by the distribution of the HF1, HF2, HF3 in that case. Okay, and that is why you need to use the quantization of the energy to fit the curve instead of a classical one. Classical one, they give you the continuous distribution of energy. So when you try to add the contribution, they just easily just went to the infinity. So there's no way you can solve the problem based on the classical physics. So this is a very intrinsic and a very big step forward. So the Planck proved that his assumptions can be used to understand the black body spectrums. And also, he also pointed out that because the Planck constant h he used is a very tiny number, so this is the reason that this kind of effect is not that obviously, this quantum effect is not that obviously when we study the classical physics, that is about the microscopic scale. So only when you study about the interaction among the protons, electrons, this kind of scale, then the concept of the quantum mechanics become very important. So now you probably starting to build a sense of feeling that why we need to study the quantum physics and why it will be useful for you to study the chemistry or the biology later. Even those you may not use directly quantum physics, but you'll find out the simulation you are going to learn, they are still based on the quantum effect of the particles. But for sure, when you're doing the calculation, doing the simulation, people always have to choose, is that in your systems, does the quantum effect dominate or it is negligible? Do you agree? So this microscopic situation, this one, there's no rigorous definition that, which means that how big it should be. There's no just one number there. So you have to decide a new system, which is more important. And the simple harmonical oscillator approach I show you is also just one kind of approximation approach to study the energy and the frequency of the system. In fact, people can use Hartree-Fock or any different kind of the approach to study that. But for sure, now at this class, we are not able to introduce the concept of that. But people at the moment, as I mentioned, that even though the Planck can explain the data, but people think it makes no sense. So it is until that Einstein say, okay, no, the Planck is correct, and the energy should be quantized, and this kind of state of the quantization is the so-called photons as the particles. So now the light can be quantized, and the quantization of the light is a photon, which is the particle of the light. And the energy carried by this photon depends on the frequency of the light. And the energy now is HF. And people in the third section of the video lecture, I will introduce you the photoelectric effect. So Einstein, based on the assumption of the Planck, they say, okay, now the photon is a particle carrying this specific amount of energy. Then he used that to explain the photoelectric effect. So I know that Einstein is famous for many different kind of things, but the reason why Einstein won the Nobel Prize in the 1921 is because for his achievement to explain the law, the photoelectric effect, which is the topic for the next lectures.